Okay, so when we change the widths of our rectangles, we're going to have some summations where the numbers we're plugging in are not integers. So we're going to need to just do a little bit of fancy algebra to make it so that when we plug integers in, which is the only thing the summation will accept, that we are doing it correctly. So like, for example, if you wanted to just try and write the summation from n equals 1 to 2.5, first off, you can't even do that because you can only have integer values here. So this would plug in 1, and then it would plug in 2, and then it would be lost and confused and not know what to do. So again, you can only plug in integers, and these are not integers, 1.5 and 2.5, and it moves up 1 every time. And here we're moving up by 1.5 every time. So we're going to need to do a little bit, like I said, of other work to make it work out. So the first thing that's really helpful to do is to look at what you think the function is that these got plugged into. When you're doing area, you'll have a function already, but we can see here that we're plugging x squared is what's happening. Some number is getting squared. However, as I already said, the things that are getting squared are not integers. So I'm going to just label each of these x's with a subscript. A subscript doesn't mean anything mathematical, it's just giving them each a different name. And then I'm going to make a table to see if I can find a rule for what is happening with my inputs here, my 1, my 1.5, etc. So I'm going to start with n and x sub n. So when I have x sub 0, my input was 1. When I'm at x sub 1, my input is 1.5. When I'm at x sub 2, my input is 2. And when I'm at x sub 3, my input is 2.5. So I'm going to find a rule for my x sub n. So x sub n is equal to. So hopefully we started to recognize from our algebra days that we are adding 0.5 every time here. So this is a linear function with a slope of 0.5 and a y-intercept of 1, since at 0 the value is 1. So x sub n is 0.5 n plus 1. That means when n is 0, x sub n will be 1. When n is 1, x sub n will be 1.5. So what we really want plugging in our function here with our for our summation is x sub n, not x, right? We want to be plugging in these values here, okay? But again, they're going to be rated based on the n. So if I go to write my summation now, I'm going to have a summation. I'm going to start from n equals 0 and go to 3. And what I'm going to plug into my function f is 0.5n plus 1. And now by doing that, when I plug in 0 for n, I'll get 0 plus 1. So I'll start with f of 1. I'll plug 1 into the function. Then when I plug in 1, I'll get 0.5 plus 1, which is 1.5. Then when I plug in 2, 0.5 times 2 is 1, and 1 plus 1 is 2. And then, of course, I'll keep going. And when I plug in 3, 0.5 times 3 is 1.5. 1.5 plus 1 is 2.5. So now I've changed the inputs of my function to be these decimal values that I want instead of the integer values. And so then I would have 1 squared plus 1.5 squared plus 2 squared plus 2.5 squared. Now, if you don't want to work with the function notation, sometimes if you're working in an activity maybe or something where you don't have the function separately defined, that's the word I was looking for, separately defined, you can still do this. So you can say same idea, but what you're going to say is that instead of writing f of 0.5 plus n, you're actually just going to think this x got replaced with 0.5n plus 1. That's what I want plugging into my function. So this x will also get replaced with that. So I'll have 0.5n plus 1 squared. And that just kind of allows you to skip this step here when you go to evaluate and head right down to this step here. So it depends working in Desmos. If you already have the function written out, if the function's more complicated, this notation might be easier. But sometimes if you don't want to have to define the function separately, this notation might be easier.